So we're not going to finish our lecture for today. I know that already because it's a pretty long one because we're starting another new chapter. But it's basically an extension from Monday. Okay, and today we're talking about work and energy. And let's just define what work is. Right, work is the product of the magnitude of the force. Right, and the parallel distance through which the object moves, right? So literally, what work is the force times the parallel distance. So when they say parallel distance, what they're talking about is the direction of the force and then the distance that that force traveled parallel. So if I'm like pushing a box across the way, like I'm pushing a box across the way, the parallel distance would be the distance the box traveled on the floor, right? Because the floor would be the parallel distance. Okay, we can shorten that up to say that the W, which is work, equals FD, the force times distance that the box traveled. Okay, or whatever object. It doesn't have to be a box. Okay, and so of course, mechanically, work always involves force and motion, right? A force and a motion. Okay, so let me just reiterate this. Mechanically, work involves both a force and a motion. Okay, that's important. And the reason why it's important is because your first question for today: which of the following is not true about work? And while you guys are logging in, I will log in. There it goes. Oops, wrong one. Wrong one. Close. Close, close, close. And then log in to Microsoft. Thank you for keeping me logged in. And then this is NSC. All right, we got 14 responses so far. 18 now. 22. Okay, that's good. All right. Good job. The vast majority of you got that correct. The one that is not true is literally the D answer there. I forgot to put A, B, C, and D, but that's self-explanatory. So thanks for figuring that out. So the correct answer was C here because mechanical work involves not both velocity and acceleration. What does it involve? Force and motion, right? So good job. Most of you got that right. Congrats. Did you have problems scanning this time, Carly, or did it work immediately? Oh, wow. You must have gotten your phone upgraded again. Um, so taking a look at this right here, this guy here that's pushing off the, this is how you know I came here straight from Houston. I don't have my laser, number one. And then when I look at my backpack, I still have my clothes from yesterday. So I literally came here straight from Houston. Didn't even go home yet. So, um, what was I saying? Yeah, so no work is done here, right? Because there's no movement. So the reason why that is because this guy here, right? He's pushing against this brick wall, and he's pushing as hard as he can, but it's not moving, right? And so when you have the equation here, work equals FD, he can put as much force as he wants, right, in the F. But if the distance is still zero, right, whatever F is times zero will always be zero. So the force is zero, right? I mean, sorry, the work. The work is zero, okay? So in this case right here, D equals zero, so there's no movement, there's no work done. Poor guy, he feels like he's doing work, but he's just stuck there because he's trying to push a brick wall. Why would anyone do that? Maybe he's doing push-ups or something. All right, so contrast that with this, right? This guy here, originally he had the box. Originally he had the box over here, the initial distance or position right here, right? And he was able to push it all the way over here, right? All the way over here. So since there was a distance that the box traveled, that's a number there now, D, right? Then there's also a force that he applied to it, right? So F times D equals work, and it's not zero this time. Okay? It's not zero this time. Does that make sense? Do you see the difference between the last one and this one? Right? The box is actually moving. So then we have here, this lady is mowing the lawn. God, I still need to mow my lawn. It's been like 2 months. Good thing it's getting cold. All right, so you don't know, man. My homeowners association is all about mowing lawns for some reason. I mean, they'll fine you, and if you don't pay the fines, you'll get like a lien on your house. I hate the HOA, which is funny because I'm actually a member of the board of our HOA, so maybe I should change something about them. So this lady here is mowing her lawn, okay, and um, the thing that I want you to notice here is that there's the FH, which is the force horizontal, right? The horizontal component of the force, right? And then there's the FV, okay? And that's the vertical, okay? The thing that you need to know here that is that she, as she's pushing the lawnmower, she's only going in a horizontal motion, right? She's only going in a horizontal motion as she's pushing it. But the angle that since the angle of the handle of the lawnmower, right, goes down like this, you get this force, net force pushing downwards, okay? But since she's not moving downward at all, she's not pushing down on the handles, she's only just pushing forward with the handles, right? There's no vertical force at all, there's only horizontal force, okay? So when you see a situation like this, work only equals the horizontal force times the distance, okay? It can be a lawnmower, it could be the vacuum cleaner, right? It could be all kinds of stuff like that. So be prepared on a quiz or an exam where you see a picture of somebody doing something, right? And you have to figure out the right equation, okay? Don't worry, there won't be like any numbers to put in there. I just want you to understand the situation, okay? I just want you to understand the situation. Right? So again, she's only going forward in a horizontal fashion. So if she were pushing down on it, right, like actually pushing down on it, not pushing down because she's going forward, but if you were actually pushing down, then you would have like the force V and the force H2. But she's only pushing forward, so it's only force H times distance, right? See, it even says right here, if a part of your effort pushes the lawnmower down, right? Even if that happens, right? So the she's going forward, right? And in the action of her going forward, it pushes the lawnmower down a little bit, right? She's still just doing the horizontal force. But if she were actually intending to push down on it on the handle, then there would be a vertical force. But this is who does that? Who's just it'll just make the lawnmower go slower if you did that, right? So so there's some units that you need to be aware of, right? With work. Work equals, or W equals FD, of course, which is FD, which is force times distance, okay? And the unit for that is known as either the Newton meter, right? So that's newtons times meters. And you can abbreviate that by saying N dot M, right? A lot of scientists like to be cool. And so instead of using the multiplication symbol, they'll use the dot instead. They mean the same thing, right? The dot and the multiplication symbol mean the same thing, right? So Newton meter, which makes sense because force is in newtons, right? And meters is a distance, right? Meters is a distance. And then you can also call that a joule too. You can also call that a joule. Okay? Also call that a joule. If we're talking about the British system, which is actually kind of funny because they use foot pounds in the British system for work, which foot and pound is what we still use here, instead of the metric system. But I guess for the British system, the only thing that they didn't switch over to metric was was their work the unit, right? Everything else they switched over to metric, right? So the foot pound, and I think that. I forgot. I may have asked you this before, but is anybody in here a mechanic? um, So I was talking to you before about breaker bars and like big wrenches, and you can change the torque on things, right? And it will give you, the longer you make the wrench, the easier it is to break a lug nut. Remember from a spare tire or something like that. Well, there's these special wrenches that are called torque wrenches, and what they do is that they tighten screws just the right amount. Okay, because most people when they tighten screws, they tighten it too much, and it strips the screws, and you can't use them anymore, or the bolts, right? And so when you're using this thing called a torque wrench, you can set it to the correct foot pounds, right? And it will tighten your screw or your bolt to the exact right amount of foot pounds, and then you hear this click. You go click, and then you know it's tightened correctly, and you know it's not over tightened, and you know it's not too loose, right? So that's where you would actually see this unit. You'll see this on a torque wrench. It looks just like a regular wrench, except it's got a little dial on it, and you can change numbers on it, and it can say, I want it to be 600 foot-pounds, for example. Cool stuff. So your next question is here. Which of the following is not a unit for work? Okay. All right. So I've got 25 responses. Wow, there's a lot of people here today. 25 responses. Okay, so 5 people said that the Newton meter was not a unit, and the rest of you picked D, which the rest of you who picked D are correct. All three of these are units of the of work, right? I spent a lot of time talking about that guy right there with the dot, right? So that's the Newton meter right there. Okay. And I mean, you can already predict that I'm going to have a question on the exam that's multiple choice, and it's going to be like, which of the following is not, a work unit. Okay. All right. So working against something. Okay. So when work is done, we generally feel the other part of Newton's third law, Newton's third law force acting against us, right? Gravity and friction are common agents working against work. Working against work, that's funny. And in case of gravity, we must apply the force to overcome the force of gravity, which the weight is mg, right? Remember in the last slide, we were talking about, not last slide, last lecture, we were talking about how W, or the weight, right, of somebody or something on Earth is just the mass times the gravity. Anybody remember what the gravity is again? Exactly, 9.8 meters per 9.8 meters per second squared, right? So when you're trying to lift something up, the work that you're doing, right, is W equals FD, of course, right? But then it can also be W equals uh, um, the height, W times the height, right? But really, in the end, all that matters is this one right here. Work equals the mass of the object times the gravity of the object, right? And times the height of how high it was. How high did you lift it? Okay? How high did you lift it? So you can either say work equals W, of course, but we already said before that work equals the force times distance. It can also equal the weight times the height, right? And then based on what we were just talking about before, the height is there. The weight on Earth is the mass times the gravity. And so in the end, the one that's important is mass times gravity times height. Gives you the work when you lift something up. Okay? Gives you the work when you lift something up. Okay? And just remember H is height lifted. So that takes us to energy. Okay? Energy is obviously the ability to do work, right? An object or a system that possesses energy has the ability to do work, right? When work is done by a system, the amount of energy of the system decreases. Okay? And that makes sense. Why? Because you've done work, then you have less energy, right? So it makes sense. It totally makes sense. But when work is done on a system, that system gains energy, right? So that's basically the opposite of that previous statement right there, okay? When work is done by a system, say you're the system, right? You the person, me the person, I'm the system, and I'm doing work like I am right now, right? Talking to you and teaching you. I'm losing energy each time I do it, as I do it, right? When I'm the system, right? But then when work is done on the system gains energy. So that's like me going to get a snack, right? I'm putting energy into me, right? By doing work on me, by eating, which I should eat because I haven't eaten all day today. But that's okay. I'm trying to lose some weight, so that's a good thing. But I'll eat something, and that's me doing work on the system, me being the system, and it gains energy, right? Because food gives you energy. Does everybody see the difference between those two? Those the second and third statements. Does everybody see the difference between those? Why one is a loss of energy when the system is doing work, and then there's a gain energy when the work is done on the system. And of course, again, when the work is done on the system is basically when if I were the system, I'm eating or something like that, and you're putting work into eating on myself. So work is a process by which energy is transferred from one object to another, right? Which makes sense, like that guy that was pushing the box, right? The guy that was pushing the box, and it moved, right? And so you had your energy, and you were pushing the box, and the energy gets transferred to the box, and that's why the box moves, right? That's why the box moves. And then work and energy have the same units. It's joules, right? It's joules. Joules can also be converted to calories too. You don't need to know that, but it's the same kind of calorie you think of when you're eating food. Okay? So let's talk about a couple different types of energy. Okay? We've got kinetic energy, which we've heard of many times. It's the energy involved in movement, right? The energy involved in movement. The energy an object possesses because of motion, the energy of motion, okay? But I called it movement, whatever, right? Same thing. And it's got a very simple equation. The kinetic energy of a particular object is 1/2 times its mass times its velocity squared, okay? And you're going to have to help me out with this too, because every time there's a velocity squared, I always forget to square the velocity. So make sure, make sure you remind me if I'm working any examples for you that that I need to square the velocity. I always forget about that. Okay. So kinetic energy is then excuse me, abbreviated with an E and a K for kinetic energy. Abbreviated with an E and a K. And the formula is, as you see here, basically 1/2 times the mass times the velocity squared. This is obviously when an object is already moving, right? Because if the object were stopped, it wouldn't be kinetic energy, would it? Right? It's got to be moving for it to be kinetic energy. So the object is already moving. And you can calculate the work done by that object, right? Because the work done by that object is equal to the change in its kinetic energy. Okay, it's equal to the change in its kinetic energy. So if you look over here, we have work equals delta. This is the triangle here is delta, right? So usually it means change in, right? So if you remember back in the first, I guess maybe it was the second lecture we had, I was talking about how to graph things, and I said the change in x divided by the change in y. Remember that? Well, this is going to be the change in the kinetic energy, right? The triangle means delta, or the change in the kinetic energy. How do you determine the change in kinetic energy? Right? Oh, that's so touching. Someone wrote up here, Heart Chem. That's so touching. I got distracted. Sorry. So, did you write that? Has it been? Well, that's okay. You can just lie, so I feel good about myself. Jeez. Sorry. Back. You should all love chemistry. But for some reason, I'm teaching you physics right here. So, like, what the heck, right? Anyway, so how do you figure out what the change in kinetic energy, right? You literally just take the final kinetic energy you have, and you minus the initial kinetic energy you have, right? It's the final initial energy subtracted by the initial kinetic energy. Okay. Well, how do I do that using the equation I have here? 1/2 mass times the velocity squared, right? We already know that kinetic energy is 1/2 mass times velocity squared. So literally what you can do then is substitute this equation in for each of the kinetic energies, okay? Where the second, or not the second, but the final kinetic energy equals the 1/2 times the second, or the final velocity squared, subtracted by the 1/2 times the mass times the initial velocity squared. So you see what's happening here, right? You have an initial velocity when the object is moving, right? That's not the initial, sorry, the final. You have the final velocity when the object is moving, right? And that's v2, and it corresponds to the kinetic energy 2, right? And you have the initial velocity. The initial velocity right here corresponds to the kinetic energy 1. So quite literally what's happening then is that the work is based on how fast, right, this object was moving at the beginning and at the end, right? That change in velocity is what's telling you, right? That change in velocity right there is what's telling you what the change in kinetic energy is, which is what tells you what the work is, right? Because the rest of the stuff stays the same. The 1/2 stays the same. The mass stays the same. I mean, the object didn't lose any mass, right, when it was moving. So the only thing that's different here is going to be the velocities. Okay. And assuming that the initial velocity is different from uh, the final velocity, right? Okay. All right. That's actually like a lot more math than I was intending for this particular thing, but I just wanted you to see that the changing kinetic energy, or the work done here, is quite basically dependent on what the two velocities are of this object when you're looking at it, right? So here's your next question. Which of the following, in regards to kinetic energy, in regards to kinetic energy, work equals dot 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 what? Okay, so 25 people in here today. That's like everybody. I think we're only missing like one person. I can't believe you guys are still all with me. Like, you haven't dropped the class because you hate me. You know, I mean, that could be kind of a prick sometimes. So that's why I say that. Okay, so what are we doing here? Kinetic energy work, I believe. All right, 23 people. 23 people. I'm so impressed. I am so impressed. Good job, everybody. You saw my trickery. You figured me out, right? The only one that's real is A, right? Good job, good job. What the heck is this thing? The only one that's real is A, right? The change in the kinetic energy. Both of these should be what kind of signs? Minus signs. Good job, good job. Very proud, very proud. Means you've been paying attention. I'm so excited about that. So excited. Don't worry. I mean, I know everybody hates the substitute teacher, but they'll probably be a better teacher than me anyway. So it's gonna be fine. It's gonna be fine. And you won't have all these like tirades and stuff, these like rants I have about like clean water and stuff. Okay, so here's an example. Okay, here's what chop. Okay, here's an example. Right, we have a 1 kilogram ball, and it was fired out of a cannon. Right? Why wasn't it just a cannonball? Whatever. Anyway, a 1 kilogram ball, it was fired out of a cannon. Right? What is the change of the ball's kinetic energy? Right, when it accelerates from 4 meters per second to 8 meters per second. Right? So notice again, the thing that changes is what? The velocity, right? It was starting out at 4 meters per second and it got faster. It got up to 8 meters per second. Okay? And I don't want to get hit by a cannonball, so I'm going to do the math to make sure that I don't get in the way of the cannonball. Or you could just watch and make sure you don't get in the path of the cannonball, but you could also do the math. Some people do that. Okay? Like back when I was playing softball, I used to play softball on the intramural softball team. I used to calculate the distance that the pitcher was like pitching at me, so I knew exactly where the ball was going to be when I swung my bat. I did it in my head. It's good. Good stuff. So, what was I saying? Lost my train of thought. Oh yeah. So we'll use this equation right here, right? The one I just told you about, where the change in EK equals the change in EK2 minus EK1. And so 1/2 we already have. We got the mass. The mass was 1 kilogram right there. So we'll put the mass in there, right? And this is V2, so that's going to be the 8 meters per second, right? Squared, so we'll go ahead and square that. And then the V1 here, so we put the mass in again, 1 kilogram mass, put it in there. And then we have the V1, which is the 4 meters per second, square that guy too. And that's what we get here, right? We get EK equals 1/2 times 1 kilogram times 8 meters per second squared minus 1/2 times 1 kilogram times 4 meters per second squared. Okay, so easy stuff. I would go through and I would do the square first, right? And then multiply this times this times this, multiply this times this times this, and then subtract it, right? So we get 32 joules minus 8 joules, and we get 24 joules. Okay, pretty simple on how to work those kinds of equations. Pretty simple. Okay, pretty simple. So this is also another interesting thing here, braking, right? So when I was in driver's ed, back in the day when you had to take driver's ed before you get your driver's license, right? The guy that was teaching us driver's ed was always about how if you wait to stop your car, like if you wait to brake, you're more likely to hit somebody because you need a minimum distance before the car will actually stop, right? So, and the bigger your car is, the more distance it takes to stop, right? So if you're in like a little smart car, like that's like this big, right? The smart car, it's like this big. Oh my God, so funny. So I think I told you guys that I graduated from Auburn University, right? And when I was there, we had a lot of football games and tailgating, and my boss had a smart car, and so he used to drive his smart car to campus on game days because there's literally no parking on game days, right? People are parking in the grass, parking on the sidewalks, parking everywhere. There's no parking spaces. So he'd take his smart car. So he comes into for the game one day. We're all tailgating and having a great time watching the football game. And he parked his car somewhere in front of the chemistry building. And then we come back, and his car's not where he left it. We're like, it's not parked where he parked it, right? It's like, what the hell? What happened to my car? Right? So literally, what happened was that four guys came over and picked up his car and moved it like to the spot right next to like the dumpster. And we're like, did you park your car next to the dumpster? He's like, no, I parked it in that spot where that truck is. So, so smart cars are literally that light that you can like get four people and they'll pick up a smart car. Which makes you think, are they safe to drive on the highway? I mean, like I feel like if you were to get hit while you're inside of a smart car, it'd be bad. Just saying. Just saying. I'm just saying. It seems like a smart car is dangerous. But the good thing about a smart car is that since it's so light and small, when you brake, it'll brake pretty quickly. You know, instead of having like a Ford F-350 that's going to take like a good, 200, 300 yards to stop when it brakes. Okay? Well, yeah, a car is light when you can pick it up, when four people can pick it up, right? So I'm surprised they didn't like tip it on its side because it's also very tall looking too. So anyway, so you can calculate, you can calculate how far, right? You can calculate how far it will take for an object to stop, right? Based on the work equation. Okay, so the work to stop, an auto or a car equals the braking force times the distance again, right? Times the distance. So again, kinetic energy here, right? Where the formula is 1/2 mass times the velocity squared. Okay. So we know that work equals FD, right? The force times the distance. We also know that the work equals the 1/2 mass times velocity squared, right? So you can put the two together and get force times distance, right, equals 1/2 meters per second squared, right? And so you can plug in the force here that you used to apply on the brakes, the mass of the object or the car that you were driving there, how fast you were going there, right? And then you can figure out how far it will take you to stop by solving for distance. It's crazy, right? I bet you're thinking about that every single time you brake on the highway, right? Every single time. Okay? Every single time. So, since F, M, and 1/2 are all constants, that means it doesn't change with the car, right? It doesn't change with the car. Um, I think cars will actually have in their, I mean, I don't know anybody who actually looks in their user manual of their car these days, but if you look in the user manual of your car, it will tell you the braking force your car has, right? How much force your brakes actually have, right? And so the reason why force is constant, it doesn't change. That's because that's a manufacturer, specification on your brakes. Okay. The mass of your car doesn't change, right? So like I guess unless you get hit and then you lose like your bumper, then they'll change. But normally the mass of your car doesn't change, right? And then 1/2 doesn't change either. So the distance is proportional to the velocity, right? The distance is proportional to oh sorry, I did it again. The distance is proportional to the velocity squared, right? To the velocity squared. Okay. So the faster you're going, the longer it'll take you to stop when you brake. Does that make sense? Right? So this is the part I need you to know right here. Okay, for questions. If the velocity of the car is doubled, right, the braking distance is quadrupled. Okay? That's the important thing. Right? If your velocity is doubled, then your braking distance is quadrupled. So what that means is, let's say you were driving 30 miles per hour and you stopped, right? But then you were driving 60 miles per hour and then you stopped, right? The distance would be 4 times that of you were driving at 30 miles per hour. Does that make sense? It doesn't just double, it quadruples. Okay? So slow down out there on the road. Except that I don't slow down either, so I can't really preach what I don't practice. So do your best on the road. Try. Try to be safe on the road. This is even crazier. If the velocity is tripled, then the braking distance is what times 9. What do you say? How do you say times 9? Not quadrupled. Nine nupled? Nine nupled? Non nupled? Yeah, non something. But it's 9 times the distance, right? 9 times. And the reason why it's doing this is because it's a squared, right? It's an exponent. So it's not just going to be 2 like double, but it's going to be 2 times 2 squared, right? That's why it's 4. And here it's triple, right? It's not doubled because it's not 3 times 2, which is 6. It's 3 squared, and that's why it's 9, right? So say you were going quadruple the velocity, right? If you're going quadruple the velocity, what would be the braking distance? 16, exactly. I mean, I was going quadruple the velocity this morning trying to get here, right? Well, I think I was going like 110 on 45. No, I'm just kidding. I wasn't going that fast. That's why it took me from 6 o'clock to um, noon to get here. Okay, so yeah, does that make sense, though? Right? Okay. So here's your next question: if the velocity is doubled, the braking distance is what? You can see that like what I'm presenting to you now and teaching you now is very conceptual, right? I really want you to understand what's happening in certain situations and demonstrate to me that you understand what's happening, you know, instead of actually just plugging in numbers. Does that make sense? And I'm sure most of you are very happy about that. All right, so we have braking distance. 23. Wow, you guys are really fast today. You guys are really. It must not be asking you to like sign in multiple times. Good job, good job. The vast majority of you got that right, right? Vast majority of you got that right. The velocity is definitely quadrupled when you double the speed. Okay, double the speed. Just remember though, as you like for future questions, I might ask you, what if you're going, 20 times the speed, right? Then what it's going to be? It's going to be 20 times 20, right? Or 20 squared, and that would be how much distance it takes. Does that make sense? Right? So it's good stuff. Good stuff. Okay, that brings us to talking about then potential energy. So potential energy is the energy when you're like just staying still, right? Like the object's not even moving. The object's not even moving. Okay. The energy of an object has, because of its position or location, the energy of position, right? So that's like that's like if you were to lift again, we did some work when we put in the work to bring this bowling ball up. We picked up a bowling ball up high, right? We put in the work, right? And so when we put in that work, it's just like I was talking about before. You have put energy into the system, and the system is a bowling ball, right? And since you have it up this high, this bowling ball now has potential energy because you put energy into it. Does that make sense? Right? You put energy into the system. The system was the bowling ball. It's up high and it's potential energy. And it releases that energy when you do what? You drop it, right? You drop it, and then it breaks the floor, and that's where the energy went. It broke the floor, right? Okay, good stuff there, right? So most potential energy is due to gravity, like I just said with the bowling ball, right? Remember that in potential energy, work equals the force times the distance. We've seen that many times, right? So W equals FD, right? Of course, the weight again is a force, right? And the weight equals, on Earth especially, the mass times the gravity. Okay? The thing that changes here is that instead of using D, right, for when we were pushing that, remember we were pushing that box across the way, right? There was actually D here involved. We're going to switch out the D now for H. So now work equals mass times the gravity times the height. And that's literally the height that you lift up something. Okay? That's the height that you lift up something. So if you just wanted to do the gravitational potential energy, right? That's basically the weight times the height. It's the same thing, weight times height. So overall then, your potential energy equation was mass times gravity times height, right? Contrast that with the kinetic energy equation. Remember, it was 1/2 times the mass times the velocity squared, okay? And the reason why that is because the kinetic one, you're moving something, right? The thing is moving, and it's going at speed, and then it's going at another speed, right? And that's why you have the velocities, right? But here, when we're talking about potential energy being most dependent on gravity, you don't really care about if it's moving from side to side anymore. You care about how high it is when it got dropped, right? Does that make sense? So let's look into a little more deeply the gravitational potential energy. Okay, the gravitational potential energy. What slide? Oh man, there's 59 slides on this PowerPoint, and I'm only at slide 17. We're definitely not going to get finished today, but that's okay. The substitute teacher will teach you the rest of it. I'm sure you're looking forward to that. So, the gravitational potential energy is equal to the work done, and this is equal to the weight times the height, right? So it's basically restating it again, right? EP equals mgh. So here's our example, okay? How much work is done when lifting a a 1 kilogram book to the height of 1 meter? It's very simple, right? We get the weight of the book right there, which is one kilogram. Put it in right there for the mass. We all already know if there's one thing I want you to take away from this class when we finish, it's gravity's constant, which is 9.8 meters per second squared, right? And you multiply it by the height it was at, which is 1 meter, right? And you just multiply across, and you get 9.8 joules, right? 9.8 joules. So this is also, not only is this the work, right? But remember, work equals EP, right? So this is also the amount of potential energy that the book has at 1 meter height, okay? So it's not only the work, it's also the amount of potential energy the book has at 1 meter of height, okay? All right, so let's look at a picture now, okay? So potential energy, it depends only on the initial and the final positions, right? Basically the difference in height, okay? It is independent of path, which is what I was saying to you a second ago, right? It doesn't matter if it's swaying back and forth as it's going down. All that matters is how high it was when it started, and it's going to land on the ground, right? It doesn't matter if it's going back and forth, okay? So if you have this box here, well, let me finish reading. If we disregard any frictional loss, it takes the same amount of work to lift the mass, no matter what the path, right? So here, right, we have a box that's on a table, Maybe it's my Amazon package I ordered, right? And my dog jumps onto the table and knocks it over, right? It's gonna fall this height right here, right? So mg stays the same because that's the mass of my Amazon package, and then gravity stays the same because that's the 9.8 meters per second squared, right? EP equals W, which equals mass times gravity times height. So that's the height, right? But then you look over here, maybe my dog was getting a little bit rambunctious with the box and decides he wants to throw it off the thing, right? Like grab it by his teeth and throw the Amazon package off. And so instead of just falling straight down off the table, it flies over here or it flies over here, right? Well, it doesn't matter because the height that it fell is still the same, right? The height that it fell from is still the same. So the takeaway message from that is that no matter what the path the box, the Amazon package travels, right? The height that it falls will be the same, right? And I was going to say something else, but then I forgot. So yes, the, the height stays the same. Okay, mg will stay the same, and the height will always stay the same. So it's always mgh. Okay, it's always mgh. So this is your next question. Which of the following is not true about potential energy? W equals FD. That's work. Work equals FD. Weight equals mg. Substitute W for D, or all the above is true. Which of the following is not true? Okay. That guy's going to take a lot of time to break. Very long distance. We're almost there. Just waiting on 3 more responses. We're at 22, 23 now. Okay, everybody's in. Again, I am very proud. The vast majority of you got it correct. Because what are we substituting D for? With height. Exactly. Not with, but with height. Right? In potential energy, we are substituting the D with H. Okay? We're substituting D with H. That's important. Okay? Good job, most of you. Good job. Okay, so work equals the change in potential energy, right? Work equals the change in potential energy. So here we can do this thing where work equals EP, which is potential energy, which also equals mgh, right? Which also equals mgh delta, mg delta h, the change in potential energy. Okay. So before, when we were talking about it, we were just talking about the height of where the object was, but really the equation should be the change in its position, right? The change in its height. Work is done when there is a change in its height, right? So therefore, there must be a reference point for measuring heights. And it's arbitrary, but it must be internally consistent. It must be internally consistent. Okay? It must be internally consistent. But it makes sense though, because you're talking about height, the object is, say it was at 5 feet tall, but when you dropped it, it started out at 5 feet tall, right? But then it ended up at 0 feet tall when you dropped it. So really it's not a height, but it's a change in height. Does that make sense? Right? So oftentimes when you do this, it's pretty simple because the initial was 5, right? And the final was 0, and then it's like 0 minus 5 is 5, right? Wait, 0 minus 5. No, 5 minus 0, 0 is 5. So that's height, right? So it's supposed to be changing energy. Okay, so let's take a picture of what this is. Take a picture. I mean, let's look at a picture of what this is. Okay. Um, the reference point. No matter which scale you use, delta H is always going to be the same. Okay, delta H is always going to be the same. So here we have the reference being 0 in the middle here, right? So here's 0. Here's so we always think of the up and down, the vertical being y, right? So if you're at 0 and you go up, that's plus y. When you go down, that's minus y, right? And you go minus 10, minus 20, minus 30, minus 40, minus 50 down. But then you can go positive 10, positive 20, 30, 40, 50 up. Okay? So when you have that at 0, that means your reference point is here at 0. Okay? And so when you drop something above the 0 and you hit the reference point, that's a positive height. But say I'm standing on the table, right? I'm standing on the table and I drop it. The ball is actually going to go further, right, past that 0 mark down here to the negative, right? So what that means is I can be standing on the table, I can drop it, the ball, and the ball can land on the table, right? And that would be it stopping at 0. But instead of dropping next time when I'm on the table and I drop the ball, instead of it falling onto the table, it falls onto the floor instead, right? And that would be the negative height. Does that make sense? Because it's actually gone lower than its initial or its final, right? Does that make sense? So the thing to notice about this though is that even though I have the reference 0 here, right, I can actually make the 0 down here too, at the bottom, okay? And here I'm going 0 to 1, 2, I mean 0 to 1, 0 to 10, 20, 30, 40, 50, 60, 70, 100, all the way to 100, right? But the key here is that whether I'm going to 50 to 100 or 0 to 50, the height is still what? It's still 50, right? So it doesn't matter where the reference point is, right? It doesn't matter if the 0 is here or the 0 is down here, right? The height will always stay the same. The change in the height will always stay the same. Does that make sense? Cool, cool. So these are a couple of experiences. There's only 2 things on that. Fine. Here are a couple of examples of other kinds of potential energy that don't really deal with height, right? With gravity. When you have 2 springs, when you have springs compressed with each other, and you let the spring go, that's potential energy, right? But when you have it compressed, it's potential energy still, right? But when you let it go, that's turned into kinetic energy. The other thing that's also an example of potential energy is a bowstring, like on a bow and arrow, right? Once I was at a crime scene, and we were inside the house. This was out in like the boondocks, and we were inside the house processing the crime scene of this like murder suicide. Okay, me and my friends or my coworkers, and we had a state trooper that was watching the crime scene for us, which is good because you're supposed to have a state trooper or some kind of police officer watching the crime scene for you so that the suspect doesn't come back to kill you, basically, right? But since this was a murder suicide, the suspect was dead. But the cops still wanted to be there anyway. Okay, so since we were out in the boondocks, the cop found like a bow and arrow out in the backyard and like these huge bow targets. And so here I am like dusting for fingerprints, picking up shell casings from bullets, and I hear, I'm like, what is that? Is somebody shooting an arrow at us? And I hear another, you know. And so both me and my partner go out there, and literally the state trooper is out there like practicing with that guy's bow and arrow, shooting at the damn the bow target, right? So I guess I'm thankful he was there. I guess. Oh man, he was not bad at it either. He was not bad at it. But anyway, when he pulled that string back of that bow, right, and he held it back here before he shot the target, you know, when he was supposed to be watching the crime scene, making sure we were safe, When he was holding it back here, that was potential energy, right? And then he let the string go, and it moved, made the arrow fly towards the target, right? And that's the kinetic energy. Make sense, right? An example of springs would be like a jack in a box, right? You have a jack in a box, and the jack is inside the box, and you're turning the thing, right? You keep on turning it, but inside there's a head, or maybe an entire body. Is it a head or an entire body? It's a body. Yeah, you're right. It is a body, and it's compressed the spring in there, right? And then when you go for a few minutes, and then the hatch opens, the spring gets released, and the jack in the box flies out, right? And that's the jack in the box being inside of the box, right? Is the potential energy, and when you open the hatch and it flew out, that's the kinetic energy. Okay. Now this one's a little tricky here. Okay, this next question is a little tricky. What is another example of potential energy? This is a little tricky. Tricky, tricky. Are you guys excited about your substitute teacher next week? I mean, I know I'm a unique character, but maybe you need a more traditional professor anyway. You like my what? Sometimes my stories have to be deleted from the video. Dang it, I think most of you got this right. I'm really proud here. Right? I'm really proud. This is good times. Is what this is. This is good times. All right. Everybody has answered, and I'm very proud. The vast majority of you said all of these are examples of potential energy. Right? Let's go through each one to think about this. Right? We have water being held back by a dam, which makes sense because Hoover Dam. I got when I used to drive from Los Angeles to Nevada to Las Vegas all the time. We'd always go over the Hoover Dam, and I mean that dam is huge. Number one, and it's holding back a ton of water. When it opens up the dams, the water flows through the holes and it turns turbines, and it actually creates electricity for like the entire state. So that's definitely what potential energy, right? Because that water is being held up high and it's falling down like a waterfall and it's making turbines turn, right? So that's pretty cool. So energy found in a chemical bond, that's definitely potential energy. And the biggest example of this is adenosine triphosphate, right? ATP, the 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 energy of your cells, as they call it, right? ATP begins as adenosine triphosphate, which means it has 3 phosphates on it, right? But when you need energy, what happens is that one of those phosphates breaks off, right? And it breaks that bond and it releases tons of energy. It helps you run faster. Say you're being chased by a bear, right? And you got to run because you're being chased by a bear. I mean, tons of ATP is breaking to make energy for you, right? Um, and so that's definitely potential energy because before it broke, that energy was inside that bond, right? And it was not moving, okay? But then a bear attacked you and you had to go, right? And so it started breaking those bonds and it gave you potential energy. So not only did you start moving because of the bear, right? The bonds started breaking too and movement happened and you got those energy. And then the yo-yo, of course, before it's released, because you had the yo-yo at a certain height, right? And you let go, it went back down, and the string brings it back up. And so when it's going down, that's definitely potential. I mean, sorry, when it's up there still, when you still haven't let it go yet, it's still potential energy, right? So all these examples are true. Good job. That ends today's lecture. Have a wonderful weekend.